In this video, we'll discuss post-hoc tests for the analysis of variance. Now, I'm not going to hold you responsible for knowing the calculations and being able to do the calculations. I think knowing the calculations for the analysis of variance is enough for this chapter. And when you go on and you do statistical analysis via SPSS, you'll do post-hoc analysis that way. I think it's important to understand what a post-hoc analysis test is, and so that's what we'll discuss. In your MindTap problem set, there are two problems. I believe they're 10 and 11. I'll go back and double check. You will not be held responsible for those. So yes, you'll do them, you'll get them wrong, or you can try your best to follow along with their calculations, but I'll go back and I will forgive those. I can't do it on the front end. I have to do it on the back end and dismiss those points. So just keep that in mind. So when we do our analysis of variance and we get our F ratio, it's telling us that there's some sort of difference between the groups. But when we have three groups, we don't know which ones are actually significantly different from each other. Is treatment 1 different from treatment 2? Treatment 1 different from treatment 3, that should say, and treatment 2 different from treatment 3. Which one is different, or are they all different? So that's where we do post-hoc tests. So those are follow-up tests to determine exactly which mean differences are significant and which ones are not. So a very common test is the Tukey's honestly significant difference. Now, remember we said previously that we could do a t-test. We could do a t-test to compare, treatment 1 from treatment 2, treatment 1 to treatment 3, treatment 2 to treatment 3. But that's going to increase that experiment-wise error. And what these post-hoc tests do is they try to account for that so that doing these individual comparisons doesn't increase that experiment-wise error. So honestly, a Tukey's honestly significant difference test, or Tukey's HSD, determines the minimum difference between treatment means that is needed to claim statistical analysis. So that's the honestly significant difference. So in order to do that, we need to find this Q value. And the Q value in table B5, I couldn't get it uploaded into the lecture notes in a timely fashion. K, we need to know the number of treatments in the overall experiment. So we know that we had, and that's going to be the columns of the table. And we know we had 3 treatments. And then we also need to know the degrees of freedom for within, because that's in our numerator here. So that's n minus k, which was 12. So going back to our example here, we go and we look in the table. If you wanted to look in table B5, page 542, you go to K, the number of treatments was 3. You go to our degrees of freedom for the error term, which was 12. That gives us a value for Q of 3.77. So we know that value, so we can plug it in here. 3.77, the square root of mean squared for within was 1.33 over. We plug that all in, and that's going to give us a value of 1.12. So we look at our means, and we can say that treatment 1 is significantly different from 2 and 3, but there's no difference between 2 and 3. Another test is the Sheffey test. And although I'm most familiar with the Tukey, the Sheffey is supposedly the safest of all potential post-hoc tests. It's the smallest risk of type 1 error, and it uses an F ratio to calculate the difference between 2 treatment conditions. So you'd have to go back and recalculate your sum of squared between treatments between treatments value for just 2 groups instead of 3. And one last thing. It's important to understand the relationship between the F value or a t-test, and they're always going to result in the same decision. So when you only have 2 independent samples, you can use either, and the F value is basically going to be t squared. So for any value of alpha, t critical squared equals your F critical value. So just keeping the relationship between those 2 analysis